Okay, so I would first like to thank the organizers for organizing this wonderful workshop where there are so many experts from different aspects of singularities and their resolution. The work I'm going to speak on is based on more than a decade of effort of various people here, and the names in the red are my PhD students who have contributed to this work. I'm going to talk about what is the status of the singularity resolution in the quantum cosmology. You heard a lot about the Wheeler-DeWitt quantum cosmology from Klaus Kiefer's talk. He essentially has done, he has set a beautiful stage for me to really assume whatever we know about the Wheeler-DeWitt theory and apply it to the loop quantum cosmology. So let me give you the outline of my talk. I'll give you a very brief introduction and an overview of loop quantum cosmology. Then I'll come to the main result of loop quantum cosmology, which was essentially found 10 years ago about the quantum bounds. Then I will tell you about how we have tested the robustness of this bounds with new and efficient tools for numerical simulations. Essentially, like our idea is to not only answer whether the singularity is resolved or not, but to find rigorous physics of singularity resolution. Very similar lines to what David Garfinkel, Beverly Berger, Jim Eisenberg had done for classical singularities. We want to come to that kind of a rigor in quantum spacetimes. So singularity resolution is not so difficult to achieve, as my friend Martin also said. The main point is what is the detailed physics. The details really matter. And that is what I'll try to convince, that though we are still far away from the final answer, we are moving steadily ahead. Then I'll give you various examples with various initial states in presence of a potential and in presence of anisotropies. And isotropies were covered earlier, about like 7 years ago, and people from Warsaw also contributed. What we have done is to make it much more, made the machinery to make it more rigorous. Then I'll come to some sort of a counter example in my talk, which is a possible singularities in loop quantum cosmology, which is where Professor Krolak's work becomes very interesting in loop quantum cosmology, and I'll show you that these are just weak singularities. And then I'll end up with open issues and some very important open issues and future directions. Okay, so symmetry reduced spacetimes like the mini superspace setting, the Wheeler-DeWitt quantum cosmology or loop quantum cosmologies, they can be done not with great difficulty in the isotropic cosmological models, Bianchi spacetimes, Schwarzschild interiors using Minkowski sets and so on. They provide a very tractable, very non-trivial and rich setting to implement techniques of full theory of quantum gravity. We do not know full theory of quantum gravity, or let us say loop quantum gravity here in particular, which I'm going to use. But we know enough techniques of loop quantum gravity to quantize these simple spacetimes. So doing these spacetimes is essentially like a kindergarten to learn valuable lessons, hopefully valuable lessons in quantum gravity. So what can you do in this playground, this kindergarten? A lot of things, as I will show you. You can do a rigorous construction of mathematically and physically consistent models of quantum spacetimes. It is also quite easy to write inconsistent models, which have been written down in loop quantum cosmology also and have been destroyed. You can develop and rigorously test different tools, numerical tools, mathematical tools, and you can find those techniques to extract reliable physics. Now these tools may be useful, may not be useful for full quantum gravity, but the hope is that they will be partially useful. And then you can understand potential quantum gravity implications for singularity resolution, which I'll focus on, early universe physics, some parts of it which Martin talked about, and other people like Ashtika, Reguyo, etc., and Edward has done, and black hole physics, which Bode Pulin would have talked about, but he's not coming because of his flight issues. The main caveat, which is very important to state, generally, unfortunately, like in my community, people do not state all the caveats carefully. I'll try to be as clear as possible, and if some assumptions are not clear, please ask me. The main caveat is that when we are doing quantization of homogeneous spacetimes, we are doing quantum mechanics of spacetime. We are not doing QFT of spacetime. There is a huge difference between doing QFT of the spacetime, which is the full loop quantum gravity, and doing quantum mechanics of spacetime. Why we did that? Because we don't know the QFT of spacetime. We only know some techniques of that QFT of spacetime. And assuming homogeneity of the spacetime, various hurdles of full quantum gravity, be it loop quantum gravity or a fine quantum gravity or string theory, for example, they can be bypassed because you are dealing with a lot of symmetry. Now the hope is, and that's the main caveat, that some qualitative aspects are captured. There is no claim that there is a genericity or the picture will not change. Things will change. I'll be very surprised if things don't change, but some qualitative aspects will be captured. And though it can be very tempting to build bottom-up approaches where one has learned from some qualitative aspects to gain insights about the quantum field theory of the quantum space-time, since you have bypassed various hurdles because of the symmetries, there can be many pitfalls, and I will show you later in my talk what can be the potential issues. So one has to be very careful when one is trying to talk about the QFT of the space-time. I'm not doing that. My main assumption is I'm doing quantum mechanics of space-time, and hopefully we'll learn something. So what is loop quantum gravity? Loop quantum cosmology in one slide. Loop quantum gravity is a non-perturbative background independent quantization based on astrological variables given in 86. The main variables are not metric or the extrinsic curvature, but the connection and its conjugate triad. The connection is essentially like a vector potential of electrodynamics, and the triad is like the electric field. The high mathematical precision was achieved thanks to the work of several people who are listed here in the 90s. The main result of all this work is that at a kinematical level, classical differential geometry is replaced by quantum discrete geometry, and Jurek Lewandowski, Thomas Thiemann and collaborators have shown that the kinematical structure of the theory is unique. So these are very powerful results for the loop quantum gravity. How do we do loop quantum cosmology? Essentially, the idea started with Martin's work in around 2001. The idea was to symmetry reduce the connection in the triads at the classical level and then quantize. Various kinematical features of loop quantum gravity were understood in loop quantum cosmology. The early ideas of Martin were given a solid foundation by Ashtekar, Martin and Jurek in 2003. And there were already some indications of non-singular behavior because of the behavior of the difference equations, but that was only without at the level of the physical Hilbert space. The first explicit evidence of singularity resolution in the physical Hilbert space, in the sense that physically the singularity is resolved, was done in 2006-2007 by various people in various models. Well, Martin referred to them as the exactly solvable models. None of them were actually exactly solvable models. And in fact, one can show that you can write on many regularizations of loop quantum cosmology, and they will be severely restricted if you just ask the right question. That you should get the IR limit as GR, and you should get the singularity resolution at a well-defined curvature scale. If you ask these two simple questions, you find that there is only one choice in the isotropic models, and that was given by these people in 2006 when I was a postdoc at Penn State. Let me come to some details of the gravitational part of the Hamiltonian constraint, which is the main tool to find these quantum gravity modifications. We are looking at the Ashtekar variable. So this is the gravitational Hamiltonian constraint. This is the only non-trivial constraint left. Everything is fixed because of the symmetries. N is the lapse here. FAB is the field strength of the connection, and E's are the triads, and this determinant of E is like the inverse, reminiscent of the inverse volume here. So when you quantize this theory, you essentially get two kinds of modifications. First are the curvature modifications coming from the non-local nature of the field strength. And this field strength is constructed from the holonomies of the connection. And what we understand now in last 10 years is that this is the piece which is primarily responsible for singularity resolution through various works. Now, for spatially flat models, under certain assumptions, you can capture the singularity resolution effectively by using trigonometric terms, which you also saw before the lunch. But such a naive replacement can be very misleading, especially if you have spatially curved models or anisotropy. So one has to be very careful. The second modification comes from the inverse triad terms, which were the ones which were used earlier, like pre-2006 physics of loop quantum cosmology. And here, we did a lot of interesting work. For example, like Martin, me, Roy Martins, and Ritupon Goswami, we showed that if you have these just simple modifications, and if you have an Oppenheimer-Schneider collapse, then there will be a black hole mass threshold which will form. Pankaj, me, and Ritupon showed that there will be similar Oppenheimer-Schneider collapse, there will be no naked singularities. But we found around at that time that these modifications are not tied to any curvature scale, and they actually do not make sense unless your intrinsic curvature is non-vanishing. It's simple to understand because these are tied to inverse of the scale factor, and the scale factor has no meaning if you are in a spatially flat universe. But if these modifications are the ones only present in k equal to 1 universe and the holonomies are switched off for some reason, then they can by themselves lead to singularity resolution. So this is also true. Okay, so now let me come to the strategy to extract reliable quantum gravitational physics, and this is quite demanding, but if you have more demands, I'd like to add them here. So the first task is that once you have done all your kinematical structure, you have to find the physical Hilbert space. As Professor Clowder also stressed, like everything sits in these terms of the self-adjoint operators, inner products, and the physical states. That's where the real physics is. Then you have to find Dirac observables or the relational observables to do relational dynamics. As Claus stressed, there is no notion of time in this picture. Everything is relational. So you have to find the relational dynamics and make sure that your Dirac observables are self-adjoint with respect to this inner product. So everything has to be consistent. Then consider physical initial states, such as you can choose in the GR epoch and evolve them using the quantum Hamiltonian constraint. Now, almost on all occasions, the models are not exactly solvable. They are far away from exact solvability, and therefore numerical simulations become very important. And this is what has led to the field of numerical loop quantum cosmology, in which my friend Tomasz Pawlowski has essentially played a very important role, and now we have our own groups working on it. Then once you have done these numerical simulations, you compute expectation values of observables and their fluctuations. Then you know what is the classical trajectory you started with, compare with the classical trajectory, and obtain departures between GR and LQC. I'm using now the abbreviation which means loop quantum cosmology. Then you can make precise statements or try to make precise statements about singularity resolution occurs, not only like whether the wave function dies or not, what are the expectation values, but find the observables for curvature, for example, or energy density, and try to predict what is the curvature scale at which things change. And this you can do by using energy density operators, expansion and shear scalars, curvature invariants, all those things, and then extract robust predictions. So let me give you a very simple example. This is not an exactly solvable model. It can be made so, but not in this form. So there is a massless scalar field in a spatially flat FLR W universe. We know how to solve this very simple system. The classical similarity is inevitable. Equation of state is equal to 1. There are disjoint expanding and contracting trajectories in classical. Once you quantize this completely, the quantum Hamiltonian constraint takes a very simple form, like of a Klein-Gordon equation, where the scalar field x plays the role of time in the Klein-Gordon equation, and theta is the quantum geometric operator, evolution operator, which is coming from putting h psi equal to 0, and this theta turns out to be a difference operator in the sense that this wave function is talking to the other parts in the uniform steps of volume, and these are those pieces of those difference equation. So the important thing to notice here and remember is that the discreteness is completely fixed by the underlying quantum geometry. This is in the Planck volumes. This V is in volume of the universe in Planck volumes. Phi plays a role of internal time. It is monotonic. We know that in this simple model, and it gives you nice relational dynamics. You can check that theta, this evolution operator, is positive definite and self-adjoint, so you can do unitary evolution. And you can find the Dirac observables, the momentum of the field, and the volume at a particular instant of time. The important thing to find is that this quantum difference equation which you find from loop quantum cosmology, when you are at small space-time curvature, which means that you are at large volumes, it gives you the Wheeler-DeWitt equation, which Claus was having in his slide. So away from the Planck scale, the Wheeler-DeWitt quantum cosmology becomes a very good approximation to loop quantum cosmology. Okay, so now we can choose some states psi, and we can evolve these states backwards towards a Big Bang. So we will choose a sharply, when Tomasz and I were doing these simulations in 2006, we chose simple Gaussian states to begin with, sharply peaked states, and we started evolving them towards the Big Bang. So what happens then? What happens is that if you take these states, this is a plot between the time, which is played by the role of scalar field, and the volume of the universe. You take your state somewhere here, far away, quite far away, and if it was going in the Wheeler-DeWitt trajectory, then it will keep following this blue curve, which is a GR curve, and will go into the Big Bang here. The blue curves are the disjoint GR curves, but what we found was that when we take this state and we evolve backwards towards the Big Bang, the state actually bounces and latches onto the contracting universe. And this is without any fine tuning. And we were very puzzled with this result for almost 2 years. And some of our friends were also trying to disprove it by saying that maybe the codes are bugs or these have something to do with shallow water equations, but all survived. And it turns out that there is a for the sharply peaked states, the states which are sharply peaked in the macroscopic universe, these were always numerically found to bounce at a value which turns out to be this 0.41 Planck density. And this delta is the minimum eigenvalue of the area operator in loop quantum gravity. So, and this 0.41 occurs because you have to fix a parameter called emergency parameter using black hole thermodynamics. Now, for such states, and only for such states, and under certain assumptions, which have to be emphasized, the bounce can be captured by a modified Friedman equation, which takes this particular form. Not necessarily for all states, not necessarily in different matter models, but at least for this matter model, it can be done. And for sharply peaked states, it can be captured like this. And you can easily see from this modified Friedman equation that when rho will become equal to rho max, the Hubble rate will vanish, and there will be a bounce which will occur here. Now notice also here that this volume is quite large. It's not Planck volume at which bounce is occurring, but the density is around Planck density. So the Planck volume and Planck density do not have that linear relationship. You can have it depends on how much density you are starting with to hit the Planck density. Now let me take another example, another non-exactly solvable model, which is a very nice result, a massless scalar field in K equal 1 universe. Now it seems like a very small change in the classical theory because you are adding a spatial curvature, but when you look at the quantum theory, there is a huge change because your theta, the evolution operator spectrum, becomes discrete now, and it causes various issues in normalizability. But all that was fixed, especially thanks to this very important work by the Warsaw group, Jurek Wojtek and Lukács at that time. And what happens is that again you can do the same experiment. Like the nice thing about the K equal 1 universe is that there is a big crunch singularity in the future and the Big Bang singularity. There is a big crunch in the future and Big Bang in the past. So there are two singularities loop quantum cosmology has to resolve. But not only that, loop quantum cosmology should also have a great agreement with GR at large scales. And that should come that it should predict the right recollapse point for K equal to 1 model. If it doesn't predict the right recollapse point, then the theory is wrong. And what we find here is that you start from the same states, the expectation values turn out to be in great agreement with the classical trajectories in each branch, and this effective trajectory you can't even see, like it is always lying on these red curves. Beautiful agreement. But these were sharply peaked states. And we did this, we found these cycles for, we did this simulation for about 1 million cycles, and we didn't find any departure between the effective theory and those sharply peaked states. And I should say, like there was an earlier quantization by Martin and Kevin Vandersloot. The only thing they were missing was essentially the properties of the theta operator, and this property was essentially responsible for a paper by Green and Unruh, who said that this model is unstable. But once we understood the properties clearly of the eigenfunctions, that problem automatically disappeared. Now the rigorous quantization in detailed physics has been analyzed for various models in the last 10 years. So there is an exactly solvable model, only one exactly solvable model, and that model comes that if you choose a different lapse, in particular if you choose the lapse to be the volume of the universe, then Abe and Alex Corici and I found that the spatially flat FRW model can be solved exactly. It gives many beautiful results. It predicts a minimum non-zero volume for all the states in the physical Hilbert space. You don't have to do any numerics now. You can actually do all the calculations in the physical Hilbert space. And you find that the universal maximum of energy density in the physical Hilbert space, rho max, which turned out to be exactly the same value we found in numerics. So numerics found something first, which was then later confirmed by the exact model. There is another important thing. The important question in quantum cosmology is not about the expectation values or the observers. The story doesn't stop there. You have to ask the question, what is the probability of singularity resolution? And this question can be answered if we use the approach of the consistent histories developed by Gell-Mann, Griffiths, and Hartle. And we found that for arbitrary states, even for the Schrodinger cat-like states, where one of the parts is expanding, others is contracting, things look extremely wild. David Craig and I showed that the probability of the bounce turns out to be exactly 1 in loop quantum cosmology for this model. This has to be done for other models too, but at least for this model. Now, there are many other non-exactly solvable models. Cosmological constant, both positive and negative. A lot of detailed mathematics has been, challenging aspects were studied about self-adjoint extensions by Wojtek Kamiński and Tomasz Pawlowski. Then the different permutations of these people proved various results. In the presence of radiation, Tomasz Pawlowski and Wilson Ewing have proved the existence of bounds. In the presence of potential, Abhay, Tomasz Pawlowski and me have been having this very long, like we always tell that in conferences, the results about what happens in n square, phi square potential, but there is a very new work which is coming up, which is I'm going to discuss for an aperiodic-like potential, which my ex-student and other people in LSU have done. Bianchi 1, Bianchi 2, and Bianchi 9 spacetimes have been rigorously quantized by all these people, and a lot of simulations have been already done and they are being done. Very importantly, like a lot of work has actually gone into the Gaudi models. The locally rotational symmetric Gaudi model has been quantized by these people, and there is a hybrid quantization of polarized Gaudi models where you treat the Bianchi 1, where you split it into Bianchi 1 plus inhomogeneities. Inhomogeneities are Fock quantized. The Bianchi 1 is loop quantized. So it is in that sense hybrid. This is not hybrid. This is the full quantization. Has been done by the Madrid group. A lot of extensive work they have done, which will be very useful. Okay, so now let me come to the effective space-time description, because that is something which is very important for the rest of the talk. Now you have to make certain assumptions, but under appropriate conditions, a quantum evolution can be approximated by continuum effective space-time description, and there are essentially two ways to do it. One is the embedding method, which has been developed by Abbay's students, Josh Willis and Victor Tavares, and there is another paper which is to come of me and Victor Tavares soon. And there is an independent method which Martin talked about in his talk, the moment expansion method. He already talked about the moment expansion method, so let me tell you something about the embedding method. The nice thing about this method is that it is always derived from the quantum Hamiltonian constraint in loop quantum cosmology. The connection with loop quantum cosmology is very transparent at each level. It uses coherent states. That is an assumption here, like we have to use some states, so we use coherent states. There are two main assumptions here. The relative fluctuation should be always small for this method to work. A very drastic assumption, it seems. And the state should not probe regions very close to the Planck volume. Again, also a drastic assumption. So there are tight assumptions here. And unfortunately, because of the complexity of the non-exactly solvable models and this method, which is like a variational principle essentially, explicit computations are few. But still, the method works extremely well. So there have been certain explanations. For example, like Edward Wilson and Carlo Rovelli have tried to explain why it happens. But there are certain other explanations also, which I don't have time to go into the details on. In fact, the statement is that for all the models in loop quantum cosmology where the physical Hilbert space is explicitly known, numerical simulations show that this method provides excellent approximation for initial states, which are sharply peaked at late times in a macroscopic universe. So if you believe in such states phenomenologically, as a physicist, that I live in such a universe, my universe has to be peaked in such a state, then you can very well use this effective description. Let me give you an example of the way this model can work. So there's some work in progress. It's going to appear soon. So this is a bounce in presence of a potential, a toy model, but inspired by a cyclic model kind of a thing. And here you can see, like, we again take a state far away, and this state bounces. This is the time, this is the volume. The state goes through multiple bounces, doesn't spread. And you can ask the question, how good is the effective theory? The first thing is here to really convince you, those who are not convinced, that the bounce can occur in the presence of a very non-trivial potential. The effective theory works extremely well, even in this case. I will tell you one subtlety, but the point is that this is the plot of the volume V versus phi, and I'm showing the potential also here, that the potential is not always negligible. There are also potential dominated bounces here. And this is the energy density plot, always taking the value 0.41 whenever the bounce is occurring. And the LQC curve is a red curve, the effective trajectory is a blue curve sitting below it. And as you can see, the blue curve is overestimating, or the actual quantum curve is bouncing before the blue curve, at least the peak values. So what we find here is that the quantum bounds, what we see from full LQC is in great agreement with the effective theory, but this is for the sharply peak states only so far. Now, rich physics has been explored using effective dynamics. So let me give you some examples. I'm not going to give you examples of the cosmological perturbations because that is not the goal of this talk, but some examples where singularity resolution is relevant. Singularity resolution has been studied for inflation, for isotropic and anisotropic models. Attractors have been found, probabilities have been computed. Singularity resolution also has been studied to find the onset of inflation in landscape scenarios. So this is something I'm actually very proud of, because like Garriga is essentially my friend from string cosmology, and like they actually use the loop quantum cosmology equations to resolve the singularities in string cosmology framework, and these two papers came exactly on the same day, one after another, on the same topic. The singularity resolution has also been studied in pre-Big Bang cosmology of Gasparini and Veneziano and other string-inspired scenarios. Again, Dirici is a string cosmologist, and there have been quantum Kasner transitions which we have found in Bianchi-1 model. This is without magnetic field, so there is no Kasner transition. So cigar to pancake, pancake to point, many transitions have been found for scalar field and perfect fluids. And there's an interesting hierarchy, which a kind of a periodic table which appears in these transitions. Bianchi-9 spacetimes have been studied extensively by the Morelia group, by Alex Corici and his students. And black hole interiors have been studied by various authors. Like there are results on formation of white holes, formation of Nariai spacetimes, a lot of which physics has been done. But this is under the assumption of the validity of the effective dynamics. If effective dynamics is not true, many of these things will have to be reconsidered. But this is under those assumptions. So please see, like there are different levels of things. There are things which were done, for example, here, which do not assume any effective dynamics. There are things which are here, which assume effective dynamics. So the caveats should be very clear. Now, some of the open questions which have been partially answered recently. Is bounce an artifact of choosing special kinds of initial states? Does bounce occur if the initial state has very large quantum fluctuations? Some of my friends were worried, like maybe if you have a state which has a large quantum fluctuations, it is going to completely destroy the bounce. So far, what Thomas and I had done and was done so far was only simulations with sharply peaked states. Now these states really do not probe the Planck geometry, as I showed you that we were having the bounces much earlier. Can you consider states which probe deep Planck geometry? Is the effective description still a good approximation? Due to heavy computational costs, many details of anisotropic models were only partially explored. So the Madrid group and Thomas Pavlovsky, they had done these simulations. These simulations existed in 2008, but they were not fully explored spacetimes because these computations are expensive. So how do we understand bounces in anisotropic models with as much rigor as isotropic models? Then the next question, the last question I'm going to tackle is, does quantum geometry always bind the curvature invariants, or are there any allowed singularities in LQC? So let me come to some computational costs and numerical challenges. So these numerical challenges are quite huge. Let me try to convince you. So the kind of simulations which we were doing in 2006 to 2008 with sharply peaked initial states, in these numerical simulations we were taking the outer grid, boundary of the grid for the simulations as 10 to the power 5 Planck volume, and the computational time on your good code is 15 minutes on a single core which can be done even on your desktop now. If you want to take states which probe deep Planck geometry and which have wide spreads, then since these are wide spreads, you have to take the outer volume, something like 10 to the power 12 or even higher. The problem is that this difference equation we are dealing with is such that its discreteness is fixed. And since those who know numerical relativity, they know like if the discreteness is fixed by the theory, then due to the Courant-Friedrich-Levy stability condition, you have to take finite time steps if you take the larger volume domains. That makes your computation extremely expensive. So 10 to the power 7 more spatial grid points translate to 10 to the power 7 finite time steps, and roughly heuristically translating this number makes it 10 to the power 10 years for one simulation on a single core. Okay. Anisotropic models bring more difficulties. Not only you are working with more dimensions, But what happens is that when you try to write something like a Bianchi-1 vacuum model, the simplest you can do, but probably also the most interesting one, and you write in the relational observables, you find that the equations are non-hyperbolic. They're not strongly hyperbolic. The nice thing is that my friends Wojtek Kamiński and Tomasz Pawlowski and the Madrid group, they have taught us how to actually compute all the physical wave function just by integration. You don't have to evolve anything. So the problem becomes of an integration problem, where you can take one of these V2, V3 are the two of the directions of Bianchi-1, and V1 is a conjugate to one of the directions. So you can treat V1 as your clock and V2, V3 as your Dirac observables, and you can find the expectation values. Now, this is a memory extensive job. For a sharply peak state with the values omega 2 and omega 3 eigenvalues as 1000, typical simulation takes 10 to the power 14 floating point operations. The way we do it, it translates to about 150 MB of memory for one simulation. For wider states, and if you want to probe deep Planck regime in Bianchi-1 spacetime, you need the memory of something like 5 TB. So this is essentially impossible on your desktop, even if you wait 10 to the power 10 years. You have to use high performance computing for that. So the first thing which we did at LSU was to develop some nicer methods, which is what we first call as a Chimera Scheme. Now this Chimera Scheme relies on the fact that at large volumes, the difference equation becomes Wheeler-DeWitt equation. So what we do is we carefully choose our grids such that near the Planck regime and where all the interesting physics of quantum gravity happens, we use the discrete grid of loop quantum cosmology, and later on we go to the Wheeler-DeWitt grid where the eigenfunctions are exactly matching with the Wheeler-DeWitt eigenfunction. This is a very sensitive job, but it can be achieved. Robustness can be checked, convergence can be checked, and the job which would have taken 10 to the power 10 years, if you do it correctly, will take now less than 10 minutes on a single course. So this can be achieved. So we then studied some widespread states. So this is an example of a momentum which is P phi star equal to 200. The earlier example I showed you was P phi star equal to 1000. And you can see here, if you change the spreads, this is what Martin was also referring to. If you choose your initial states differently, there are departures between the effective theory and the quantum theory. The quantum theories are these upper curves, the effective theory is the lower curve. But if you try to probe deeper into the Planck regime, the effective theory going deeper into the Planck regime, close to 10, 20 Planck volumes, then you find that there are bigger departures from the effective theory. Qualitatively, there is always bounds. This is a non-exactly solvable model which we did. Qualitatively, there is always bounds, but the point is that the very strange result which we find is that instead of these fluctuations destroying the bounds, these fluctuations are adding to the quantum gravitational repulsiveness of the bounds, and the widely spread states always bounce at smaller volume it should be at a larger volume than what is predicted by the effective theory. So this volume is always larger. This is a very embarrassing typo, I'm sorry. Okay, bounce is not restricted to any special states, so you can construct you can mix various kind of profiles and construct a very wild kind of state and then throw it on towards a singularity. And what we find is that whatever state you kind of put in, a similar state you kind of pick out, the quantum fluctuations grow near the bounds, but the bounce still occurs very nicely. And these results are in agreement with what we found earlier from the exactly solvable models. There was a lot of debate that maybe this bounce completely disappears and there is a huge fuzziness on the outside, but Kamiński and Pawlowski and Koichi and me have shown in that period that these fluctuations are very tightly bound across the bounds. Now, what is the effect of large quantum fluctuations on the bounds? What happens is that suppose you have squeeze states. So this is the eta of the squeeze states. And what we find is that if you increase the squeezeness, then the density at which the bounce occurs keeps on decreasing, and you can make it smaller and smaller. So the more quantum your state, the lesser is the space-time curvature at which it is going to bounce. So that is the kind of the general result which we are having. Now let me come to the Bianchi-1 models. And there was a rigorous quantization which we are using given by the Madrid group at that time. Singularity resolution was found there. And what we find here is if you plot these two Dirac observers, logarithm of V2 versus logarithm of V3, then the classical curve goes like this, one of the Kastner curves, for example. And the other curve is somewhere here, coming like this. And what we find is that the state actually just bounces between those two Casimir curve. So the bounce is also there in the Bianchi-1 vacuum model. There is no singularity because the singularity is completely avoided. It goes into that side. You can plot the anisotropic shear. You can find the anisotropic shear operator in the physical Hilbert space. You can plot it, and we see that plotted versus this clock B1, which goes from 0 to pi. Then this anisotropic shear is nicely bounded throughout, and the value is not much greater than what is predicted by the effective dynamics. Like, it is well bounded close to the Planckian values. For these sharply peaked states, the Bianchi-1 space-time has excellent approximation with the effective theory. But if the relative fluctuations are high, there will be departures. Now let me come to the last topic of my talk. Does LQC resolve all the singularities? What we have shown, what I've been working on, is this is assuming the effective dynamics is completely true. This may be a wrong assumption to start with, but assuming you have this picture of effective dynamics, then we have been looking at the isotropic, Bianchi-1, and very recently, just 2 weeks ago, I have looked with my student on Kentowski-Sachs space-time. And what we have shown is that there can be situations in which the curvature invariants can diverge in loop quantum cosmology. A simple example is of an isotropic model. If you write down the Ricci scalar and you use the modified Friedman dynamics, you get this expression. We know from loop quantum cosmology that rho is bounded, so there is no problem from rho. But the equation of state, if it is chosen to be exotic, like sudden singularities, then the pressure can diverge, and due to that, the curvature invariant can diverge. So since there is no control on pressure in loop quantum cosmology, pressure divergence can cause a divergence of the curvature invariant. And this happens, for example, for the sudden singularities of Barrow and Siles. Now, what is the strength of these singularities? So this is a classic work which Professor Krolak has done 30 years ago. So the Krolak's criteria of the strength of the singularity, let me remind you, is that if the singularity is at some value of the affine parameter tau equal to tau 0, then the singularity is strong if this integral of the Riemann components diverges as tau goes to tau 0. There is also Tipler's criteria. It is slightly different, but the Krolak criteria works sufficiently well. Now, Krolak also gave a conjecture, which is not probably so well known by his name, but I'm using it as a Krolak's conjecture because I found in Clark's review that it was essentially given by Krolak, that all relevant physical singularities which lead to geodesic incompleteness are strong curvature types. And it's a conjecture. I don't think any exception has been found so far, either in classical cosmology or quantum cosmology. So what happens is that in all the events where curvature invariants diverge in effective LQC, they turn out to be weak singularities. Geodesics can be extended beyond such events in effective spacetime. So it very nicely ties with the Krolak's conjecture. We find curvature invariants diverging, we find they are weak singularities. We can explicitly show in the effective spacetime geodesics can be extended. So Krolak's conjecture turns out to be true. Except one particular case, the quantum geometry always ignores weak singularities. Somehow the quantum gravity knows this is a weak singularity, it's harmless, I'm not going to touch it. Except in some cases when the spatial curvature is present, and these should be probed more, very similar to the exceptions we saw in Klaus' talk in the morning, that there are certain cases where weak singularities are not ignored. The strong curvature singularities, such as Big Bang, Big Crunch, Big Rip, Big Freeze, they cannot occur, we have shown, in the finite proper time evolution for isotropic models, for Bianchi-1 models, and the Kentowski-Sachs spacetimes. Okay, so let me come to the open issues now, and I will just focus on the most important open issue. The most important open issue was essentially posed like more than 10 years ago in this very nice paper of Brunnemann and Thomas Thiemann. Are predictions of loop quantum cosmology robust when inhomogeneous fluctuations of loop quantum gravity are switched on? And Brunnemann and Thiemann showed that the inverse triad operators, which were used in the very early works of loop quantum cosmology for many effects, including, like, I have written about 5 papers on them, they may not be bounded in loop quantum gravity. The important thing, as I stressed to you earlier, is that they do not play much important role in the bounds, and so this result does not directly affect the bounds. But I would pose that the most important open issue is to understand that the holonomy modifications, like what are used in loop quantum cosmology, do they descend from loop quantum gravity in this way, in this top-down approach from loop quantum gravity. So the question is whether loop quantum cosmology is a cosmological sector of loop quantum gravity. It's a very hard question, but it's being answered by various groups in different ways. First of all, essentially Jonathan Engel and Christian Fleischek and their collaborators in the last 8 years have been trying to find very rigorous relationship between loop quantum gravity and loop quantum cosmology. The key things are about how to deal with the diffeomorphism invariance, and there have been some new insights on that. Jurek Lewandowski, Christina Gisel, Wojtek Kamiński have shown that it's possible to generalize the construction of the APS model of loop quantum cosmology to infinite degrees of freedom in loop quantum gravity. The physics has to be analyzed, but the mathematical structure exists to study what happens to the work I did with Ashtekar and Pavlovsky in the infinite degrees of freedom. Everything exists to do that. Very interestingly, Aleski and Cianfrani have been working on a gauge fixed version of loop quantum gravity, and they have actually shown that the effective dynamics of the bounds in loop quantum cosmology appears from that. So there are, I would say, like there are very strong open issues. Everything may be wrong, what I have told you, but it seems like it is not the case. Like there are positive developments occurring on that side. So just future directions, this is my last slide. Numerical simulations for various loop quantum Bianchi models are being performed rigorously by Tomasz Pawlowski independently and Peter Diener and me at LSU. And this is a very promising avenue, I would say, for the quantum generalization of many classical results, which Beverly Berger and David Garfinkel and Jim Eisenberg proved for the classical theory. We can do that same analysis, we can repeat that machinery in loop quantum gravity. Inclusion of inhomogeneities has been going from various angles, and what is here is important is the polarized Gaudi models, which suggest singularity resolution in the hybrid model. And this is a very rich area for detailed explorations away from the Planck scale, where this hybrid quantization is going to be a good approximation, hopefully. And this can answer David's question, which he asked, like, how do we trust where do this municipal space approximation is going to be valid? How do inhomogeneities affect the main features? The Fock quantized inhomogeneities can be very useful. There are new avenues for cosmologies in spin forms cosmologies and group field theory. They are different avenues, but they have inspirations from loop quantum cosmology. And Wilson Ewing will talk in the next talk about that. And there are lots of works going on in Schwarzschild interior. Hore Pulin was supposed to speak on that, but there are lots of analytical studies which have been done by various groups. But the detailed physics is still not known, so the numerical explorations have still to be done. We don't know like what happens to, for example, like the Choptic scaling and so on, what happens in the gravitational collapse. But hopefully in the next 5 years, we'll have a lot of nice physics coming from the black hole physics. I think I'll stop here. Thank you.
Thank you very much for your talk. Questions, comments, please.
I think it was on slide 18, if you could go back. That next one, 19.
Mm-hmm.
So that's the model in which, I think you had mentioned this earlier, it's known that the energy density operator has a spectrum bounded from above by this blue line.
In SMQC, yes. Mm-hmm.
So in this case, and that's certainly consistent with the numerical results you're showing in this plot here.
But the numerics was not with SLQC.
Yeah, so there are a few terms which are different, but that's what I'm saying, it's consistent. It's not.
Yeah, so I'm not saying that it is not consistent. What I'm saying is that the constraint which we took for numerical simulations was exactly the APS constraint. It is not exactly solvable, but it agrees with the SLQC results very beautifully.
Yeah, so the question is, what happens if you showed also results in these anisotropic models over the potential?
Mm-hmm.
Do you still have the same kind of upper bound?
Very good question. So first of all, the energy density really doesn't make sense in the anisotropic models by itself, because it just captures the Ricci part of the curvature. So we have to look at both the energy density and the anisotropic shear. So in this model, this is Bianchi 1 vacuum, so there is no energy density, there is only Weil part. So the only anisotropic shear is important. And these bounds turn out to be in good agreement, excellent agreement with the effective dynamics. There is no SLQC here because there is not an exactly solvable model. So we have not done Bianchi 1 space-time with a massless scalar field right now because it's much more computationally complex, because there's an extra computational grid you have to take in phi. But at least from here, we find that if you ask the question, this black curve is the effective dynamics. So this agrees very well with the quantum values which are given by this blue and red process.
Okay, so the departures you mentioned in the last line don't affect the density, it's just the trajectory.
There is no density here, there is only an isotropic shear or expansion scalar. But the departures, I'm saying, can exist because I've also done simulations with very wide states. And in those wide states, these fluctuations will be large. And I expect, well, I have not plotted the sigma square there, but my guess is that there will be departures from the effective dynamics in that case. But again, what we saw for this case, and which you also worked on a little bit last year. Sorry, where is that plot? Yes. So what we saw in this case, here the quantum state always bounces at a larger volume than what is given by the effective dynamics. Therefore, the quantum fluctuation in the state enhance the repulsive nature of gravity. Our results show the same thing happens.
Yeah, but in these two plots, you have Eurex result, and who else too much? Who else was in there? That the energy density is bounded. So
yes.
You cannot go above the density.
No, you cannot go above. No,
Okay.
that is what we find, and that is what is surprising. Even if you add a potential, the SLQC bound.
There's a potential.
Even if there is a potential, the SLQC bound is always the universal bound. And actually, it's very simple to understand. The reason is that it was shown by Foster in late 90s that if you're dealing with potential dynamics, then near the singularity, the dynamics will be massless scalar. Very close to that. Now, in my studies with the potential, I've tried to get the bounces, potential dominated bounces, and I get them. Even then, somehow, there is something equivalent of a Foster's theorem here, which says that even if you will put all the things which you want to put in the isotropic model, SLQC bound will be the upper bound. So someone has to prove that. Yes?
He was first and then you.
Yeah, maybe you have said this somewhere in the talk, but what is the major hurdle, if any, as far as including the homogeneities is concerned once you...
Well, the major hurdle is that we do not know what is the quantum field theory of loop quantum gravity. If I want to give you the completely precise statement, Madrid group.
Technically, where does it count? I mean, what are you trying to calculate?
If you try to come from loop quantum gravity, we have very little control on the Hamiltonian constraint.
Nice. Okay.
So that is what Jurek Lewandowski, Thomas Thiemann have been trying to tackle in last 10-20 years. That is why we do not have full loop quantum gravity. But there have been other attempts, like what people have done in the Gaudi models, has in homogeneities, what people have done in spherically symmetric situations, which Horepulin would have discussed, has certain many more degrees of freedom. So the results survive there, we know that. But the precise situation, is there a bounce in loop quantum gravity, is extremely hard.
So you mentioned as sort of two separate projects, the sort of resolution of Bianchi type 1 singularities and the resolution of interior Schwarzschild singularities. But there's a very old result that in the classical theory, as you approach the Schwarzschild singularity, it looks like a particular Bianchi type 1. Mm-hmm. So, I mean, do the results of the quantum theory agree with that Bianchi 1 and the treatment of Schwarzschild? And if they don't agree, how does the quantum theory know that it's approaching a Schwarzschild singularity rather than a Bianchi 1 singularity?
That's a very good question. So to be precise, please correct me if I'm wrong, but in that case it is actually Kantowski-Sachs cosmology, which is related with the Bianchi family. Now the point is that the Kantowski-Sachs model also has a spatial curvature. And what we find is that if you have a Bianchi 1 and if you have Kantowski-Sachs, which has a spatial curvature, Kantowski-Sachs spatial curvature is extremely rich because the spatial curvature has nonlinear coupling with anisotropy. It produces dynamics which is quite different from what you will see in Bianchi 1. You can try to look at the Kastner kind of behavior, but we also find a result using effective dynamics that you may not get a white hole once the singularity is resolved, but you may get just a product of constant curvature spaces, and the space-time may never become classical again. So what I want to say is that it seems that there is a qualitative difference between how singularity is resolved in Bianchi 1 in loop quantum cosmology and how it is resolved in the Kantowski-Sachs and therefore in the Schwarzschild interior.
So, I mean, you're absolutely right about the rich dynamics. However, all the extra terms that you're talking about are precisely the ones that become negligible as the singularity is approached. So, if the quantum theory somehow notices that they're there, I mean, that's very
The difference,
interesting, and I want to understand why.
let me point out where the difference comes exactly from. In the Bianchi-1 model, if you try to look at the renormalized anisotropic shear, which you define sigma square, it's constant in the evolution. And so if you look into quantum cosmology, it will be asymptotically constant in the past and in future. If you try to define that quantity in Minkowski-Sachs space-time, even in vacuum, it's not constant, even in the classical theory. That non-constancy changes physics. So that non-constancy is because of the spatial curvature. That is where the spatial curvature is hidden. So it's not that the spatial curvature completely disappears. That non-conservation of renormalized anisotropic shear in Minkowski-Sachs has some non-trivial features.
Okay, let's sing the speaker again.